Every conventional power plant on Earth, coal, gas, fission, and most fusion designs ends the same way. They make heat, boil water, spin a turbine. The burner throws that whole chain away. It can because of the fuel. Deuterium and helium-3 releases its energy as charged particles, a helium-4 nucleus and a fast proton, both carrying electric charge. And a charged particle in motion is already an electric current waiting to be collected. That's direct energy conversion. Instead of turning fusion energy into heat and heat into motion, you turn the plasma's charged exhaust straight into voltage. No steam, no boiler, no turbine. Here's how the particles get there. They stream out along the open field lines through the plug and into the end tank, a large chamber called the expander. As the field spreads out, the beam of particles fans out with it, thinning and cooling. That expansion matters. A dense, blazing beam would tear a collector apart. A spread-out beam lands gently over a wide area. The end tank turns a violent exhaust into something a set of metal plates can actually receive. Then comes the collector itself. Picture a stack of charged grids, a periodic Venetian blind arrangement of plates, each held at a rising voltage. An incoming ion climbs that voltage like a ball rolling uphill, giving up its kinetic energy as it slows. By the time the ion reaches the final plate, it has spent almost all its energy pushing against the field. And that energy has become electric potential you can draw off as current. The faster the particle, the higher the plate that catches it. Sort by energy, collect each at the right voltage, and you recover most of what the plasma carried out. How much you recover depends on matching the plates to the spread of particle energies. A perfect match is impossible. Real beams have a spectrum, but a well-designed converter captures the great majority of it. That efficiency is not a detail, it's what makes the whole architecture worth building. In our design, the charged particle power flow is 94.56% recoverable. The fraction of the escaping charged particle energy the converter can turn back into electricity in the open simulation. It's a design figure, validated in the open, not a measured plant number. We label it that way on purpose. There's a timing story underneath, too. Particles bounce back and forth in the central cell far faster than they eventually transit out the ends. That separation of timescales is what lets a small fraction leak into the converter steadily, while the bulk of the plasma keeps burning. Add it all up. Fusion power made in the central cell, radiation and neutrons lost, charged particles caught and converted, and you get the engineering gain. That balance is the honest scoreboard. It decides whether the machine is a net source of power or a net sink. None of this works without the field that holds it together. The plugs run at 26.49 Tesla, 0.82 times a demonstrated superconducting record, so inside proven capability, not beyond it. Strong plugs make the mirror makes the beam makes the current. So the burner's power path is short and strange. Fuse, escape, decelerate, collect. Charged particles in, current out, and no moving parts in the conversion at all. This is a conceptual design, validated in open simulation, not yet an operating machine. But it's why we chose the harder fuel. Skip the steam, and you get a cleaner, quieter, more direct way to turn a